All right, there we go. 16.1, normal distribution. Consider the normal distribution shown to the right and assume that P is a point of inflection on the curve. Complete parts A through C below. Find the mean of the distribution. Okay, so let's go through some terminology. I'll explain what that bell curve is as we go. So, mean means middle, as you know, right? We've used that word before. Mean's another word for average or middle. Remember, mean was one of the three kinds of average: mean, median, and mode. There were all kinds of averages in an earlier chapter. So middle. What's the middle? Well, obviously, it's right there. It's 83. So they're just handing us that on a silver platter. There it is. The middle's 83. So I want you to read that off the graph. Find the median. Same thing. They're both different words for the middle. Finally, standard deviation. Now, what is standard deviation? Well, we've learned to calculate standard deviation in another chapter. We're not going to do that here. We're going to do something a little different. I'll explain later how it ties into what we did before. But for now, let me just say, standard deviation is the jump. And we use a funny letter. I don't know if you can see that. That's a squiggle with a little, it's an O with a little squiggle at the top there. Anybody seen that before? It's sigma, meaning it's a Greek S. Anyway, I'm not going to quiz you on any Greek stuff. This is the capital Greek S, and that's the lowercase Greek s. Whatever. It's called sigma. It's an S, in other words, for standard deviation. They use a Greek symbol. But anyway, just recognize when you see that thing, it means standard. It's an S. It's a Greek S, is what, even though it looks like an O with a squiggle. It's a Greek lowercase s. And sigma stands for standard deviation. So it's the jump amount from the middle to the first line. So how far is it from 83 to 98? So you just subtract them, 15, and that's what we got. Good? Standard deviation jump is 15. The jump from the center to the first line. Now, we don't know anything about what that first line even is. We'll get to all that. All right, let's keep moving. Okay, number 2. Find the median. That means the middle, huh? Find the middle. Okay. How do I find the middle of that one?
Use 66 and 78.
Yeah, it's the middle of these two, huh? Good. Very good, Johnny. Everybody with Johnny? That's a good idea, right? Got to find the middle of the 66 and the 78 because that'll be the middle of the whole thing. So how do we find the middle of the 66 and the 78?
Subtract and divide by 2.
Is that right? 78 minus 66 be what? 12 divided by 2, 6.
Add it to 66 or subtract it from 78.
Good job. That'll work. That's one good way to do it. There's another way, and that is, what if I said, hey, I got a 66 on an exam and a 78 on another exam? Average. That's another good way. How do you average two things? Add them and divide by 2. That's probably the quickest way. Your way's good too. Both ways are good. So let's just add them and divide by 2. That's probably the most direct way to find the middle of two things. Just add them and divide by 2, right? The average, that finds the middle. So what is that? I can't do 130. 14. What is it? 144 divided by 2? 72? So, oh yeah, obviously 72. So 72 is the middle. We good? Right there in the middle. This must be 72. All right, next question. Find the standard deviation. Well, how do you do standard deviation again? I should put this. Let me put this one up here. I'm going to move it out of the way. Scribble in. Or just rewrite it up here. Okay, so get this out of the way. How do you find standard deviation? It's the jump from the middle to the right or the left, either one. Standard deviation is the jump from the middle to the first line, either right or left, either way. And like Johnny was already telling us, we already know that's 6, huh? But if you're not sure, you can just subtract them. 78 minus 72, 6. There it is. Finally, find the third quartile. Remember Q3? We talked about third quartile before. Here we're going to use it slightly differently. I'm just going to give you a formula for it that you'll want to put on your 3x5 card for the last exam. If I can remember, there it is. Okay. Q3 is the middle plus 0.675 sigma. Hey, the middle, this right here, this is like, it's like a U with a squiggle on the left. It's another Greek symbol. It's a Greek lowercase m. It stands for mean or median, middle.
Wait, you said that should be on like a 3x5 card?
Yeah, for sure.
That little piece right there.
This formula right here.
Okay.
Yeah, for sure. So Q3, oh, and I can give you Q1 at the same time, even though we don't need Q1 right now. Q1's the same thing, it just has a minus. So yeah, Q1 and Q3, put those on the 3x5 card. This is mu, it's a Greek letter, it's a Greek lowercase m. Mu stands for middle, like the very middle, plus or minus 0.675 times sigma, the standard deviation jump. So Q1 is before halftime, right? Into the first quarter is before halftime. So that one is to the left of the middle. That's why it's minus. It's middle minus some. Whereas third quarter is after halftime, huh? So that's why it's middle plus something. See the difference? Right? First quarter is going to be like over here somewhere. Third quarter is going to be over there sometime if that's a basketball game or football game, right? Because this is halftime right here. This is Q1 somewhere over here. This is Q3, third quarter, into the third quarter, somewhere over there. That's effectively what they are. Okay, so let's find it then. So Q3, I'm not doing Q1, just Q3. So Q3 is mu, middle, which is the 72, plus 0.675 times sigma. Sigma is the jump amount, found it right there, 6. Hit the buttons on your calculator and round it, you should get 76. On that, and we're done with this question. I know none of this is too real yet. We're going to get real in a few minutes here. For now, let's just get used to using the tools, and then we'll see how they affect things in the real world, what that bell-looking thing even is. We'll get to all that. But good so far with how to mechanically find the middle, then find the jump amount, which is the standard deviation, and then the Q1, Q3, we just use those formulas to find the end of the first quarter and the end of the third quarter of the data. On that. What that means, I can say, I want to get real. I don't like putting stuff up there that's not real. That the Q3 means, the Q3, which we found is a 76. So notice it's just before the 78. See that's 78 right here. Right here, 78, 72. So Q3 is right for that. That means to the left of that is 75% of the data. Right? Just like in a football game. At the end of the third quarter, 75% of the game's over. 3/4 of the game's over. It's exactly what it means in the data. The Q3 mark is the mark. To the left of it is 3/4 of all the data. To the right of it's 1/4. That's what it does for the data, what you do with a football game. Same thing. Good to there? Questions? All right. Okay, so they're giving me the mu, which is the middle, right? 81.7. They're telling me Q3 into the third quarter is 95.2. And they're saying, hey, can you find the sigma? So what I would do is I would write down the Q3 formula. So use that Q3 formula I just gave you, which you've already got memorized, right? Mu plus 0.675 sigma. So use that formula. Plug in the Q3, plug in the mu. Can you solve for sigma? Little algebra work there. Can you solve that for sigma? So just pretend that's like an x, and you're trying to solve for x, like in your algebra days, your glorious algebra days. Those are the best days of your life. All right, so what do I do first to solve for sigma, treating it like an x? Here's the equation. Sigma's over here saying, I want to be alone. Get rid of all this stuff so I can be all there is on my side of the wall. That's what it means to solve, right? Get it alone. So that means get rid of this 81.7, get rid of this 0.675 so that I can be alone. That's what we're trying to do, right? So what do we do first to get that sigma alone? Yeah, you subtract the 81.7. Remember that from algebra? With that, boom, use calculator. What is that? Is it 13.5? Am I doing that right? Okay, good so far. Bring it over here. 13.5 is 0.675 sigma. Sigma is still saying, I want to be alone. Do I subtract the 0.675 now? Now, why do I divide instead of subtract? Because it's multiplied. This 0.675 is right up against the sigma. It's not added, so I'm not going to subtract it. It's no symbol means it's times, so the opposite of times is divide. Right? You always do the opposite. See, this 81.7 was added, so the opposite of that was subtraction. But this 0.675 is times the sigma. No symbol there. Times, so I divide it. I don't subtract it. Right? I divide it. And whatever you do to one side, you have no choice but to do the same thing to the other because you're keeping the balance, aren't you? Remember that from algebra? Do the same thing to both sides. If they were equal before, treat them the same, they'll still be equal. Cancels. Hit the buttons on your calculator. I have no idea. 20-something? 20. Straight on, 20. Okay. 20. There we go. Questions? Yes.
So wait, you put in the, what is it, sigma?
Uh-huh.
The zero, so you
Right.
put in that, or you don't? Or you
I got it alone. So I got rid of everything else that was with it, the 81.7, so that he would be alone.
Okay.
I solved for him. So I got rid of everything else that was on his side of the equal sign. All right, so there we go. Normal distribution defined by the figure to the right. Find the mean, mu, and the standard deviation of the distribution. Okay, so first step is they want me to find the middle. Don't worry about this 68%. I'm not going to do anything with that right now. Can you find the middle? So go ahead. Well, I've already found it, haven't I? So how did I come up with that? What do you do to find that middle? Add and divide by 2, right? Find the average. The average of two things. You take the 47, the 63, add them and divide by 2. It's 110 over 2. 55, yeah, that's what I got, 55. So 55 is right here in the middle. Good there. Good so far. To find the middle of two things, you add them and divide by 2. Average them. Okay, so now, second part, find the sigma. A little 0, O with a squiggle at the top. The lowercase Greek s, sigma. Find the sigma. So how do we do that? How do we find the sigma?
Find the difference between the middle and
Yeah, it's the jump amount, right? Sigma is how far. You could go jump left or right, doesn't matter. It's how far from the middle to the first line to the right or left, either way. Right, that's always what, everybody getting that? Hang on that? Because we're going to do that a lot with sigma. Sigma's the jump amount, isn't it? From line to line. Sigma's the jump amount from line to line. So you say, okay, so sigma must be 63 minus 55, which is 8. And we're done. Isn't this a great section? It's easy so far, right? It is fairly easy. It's getting harder than this, but it is one of the easier, probably the easiest section. All right. Plus, we haven't got real at all yet. Like, what are these things? Why are we doing line minus line? What in the world does that have to do with the real world? All right. Okay. Find the middle. Find the middle. So how do we find the middle? The middle's going to be the average, isn't it? So just add these two. That's 73, 73.25, yeah. And the other one, 82.75. And divide by 2. I assume by the answer here, it comes out 78. So we get, so that's the middle, 78. Okay, that was easy. Now find the sigma. Answer's already there for you, but go ahead and do it. How do we find the sigma? Sigma's the jump amount, right? Sigma's how far from here to there. So what's that going to be? 82.75 minus 78. So 2, 4, whoop, did that wrong. Subtract that, 4.75. Got it.
That's not right.
Uh-oh. Now we're going to have to stop and think. Actually, you have no way of knowing what's wrong because I haven't told you yet. So, first off, notice it didn't work. Something's different here, huh? Everybody, I mean, the first part, the average, that's normal. Nothing, no big surprise there. But this part, something's different. Something's wrong. If I was you, I'd be saying, Mr. You told us. The jump from line to line, that's the sigma. Subtract the two things, 4.75. Why is the answer 7.04? Well, because I wasn't giving you the whole story. I was keeping it simple because that's all we had for the moment. It's not always the jump from line to line. Well, I should say it's the jump from certain lines to certain lines, not all lines. There are certain special lines, and I'll get to that in a minute. But rather than get to that in a minute right now, let me just hold up for a second and notice the following thing. So it didn't work. This is not true. Cross this out. It's a deeper reason, which we will get to today. Definitely today. We got lots of time. We'll get to it. But rather than that, so that's not going to work here because these lines aren't the right kind of lines, and we'll get to why they're not in a minute. But instead, let's just go after what is true. So I don't want to talk anymore about why that's not true. We will get to that later. But what is true? How do we do this problem? Well, notice 75. I haven't been really paying attention to the percentages up to now. Now we're going to have to start paying attention. What it's saying is all that blue shaded zone is 75%. 75, right here is 75% of the bell curve. Right? Does that make sense so far? Okay, so what? As soon as you see 75% or 25% on any curve, what should you think about?
Q3.
Yeah, Q1, Q3, right? Q1, Q3. Because that's 1 quarter or 3 quarters, 75, 25 kind of thing, right? So what if I'm watching a football game? Here's the start of the football game and the end of the football game. What if I'm watching a football game and my wife calls out from the other room? She says, "Hey, what? How much of the game? Where are you at in the game?" And I say, "I've got 75% of the game still to go." That's this spot right here. Wouldn't you agree? If you're right here, it's got 75% to the right of it. After it. You with me? If I say, "Hey, I'm right here in the game," but maybe I'm using my DVR or something like that, where you fast forward through the things so you can skip all the commercials, and you're right here, and 75% is to the right. From where I'm at to the end is 75% of the game still to go. Most of the game is still to go. I'm not even at halftime, right? That's what 73.25 is, right? You're going along the bottom here. Boom, right here, 75%. Most of the curve, more than half of the curve, is still to the right. 75%, in fact, it says, right? Here's halftime. You're not even at halftime yet, right? So, in fact, exactly where are you? If I said to my wife, 75% of the game is still to go.
Yeah, Q1.
I'm at Q1. I'm at the end of the first quarter, right? That's exactly what that means. If 75% of the game is still to go, you finished 25. You're at the end of the first quarter, aren't you? So what? Well, that means this right here is Q1, and I can go grab the Q1 formula, and I can figure everything out from there. They're telling me 73.25 is Q1. When they tell me there's 75% to the right, they're saying, "Hey, that's Q1." That's what they're saying. They're saying that's the end of the first quarter because 75% of the game is still to go. You're done with 25% at that point. That's Q1, they're telling me. So I go, "Oh, okay, I got it. That's Q1, so I can do it that way, and this will work." This is how you actually solve it. You go, what's the Q1 formula? You have that in your 3x5 card. It's mu minus 0.675, so it's the minus one because it's left of the middle. And then they're telling me Q1, plug that in for Q1, is 73.25. 73.5. Mu, I got mu right here, 78, that's halftime, minus 0.675 sigma. Now I just solve that little equation for sigma, and I'll have the right answer. So let's do that. Does it make sense how I got that set up? Does that make sense? I just identified this is Q1 because 75% of the game is still to go. So that's into the first quarter. That's Q1. Wrote the Q1 formula, put in Q1 mu we already had from the previous step, 78. Let's solve for sigma. So what do we do now? We did one of these just a second ago. What do we do first to get sigma's over here saying, I want to be alone. Get rid of these things on my side of the equal sign so I can be alone. There's the wall, so to speak. Equal sign's like a separator. So what do we do first? Subtract that 78 from both sides. Gonna come up here. What do we get? That's minus 4.75 is minus 0.675 sigma. Good so far? And then divide by minus 0.675. Boom. And I'm assuming you get this 7.04 answer when you round it to two places. Positive. Two negatives divided to be positive, huh? 7.04. I still haven't explained why we can't just subtract the two lines. We'll get to that in a minute. But does everybody see that this is true, what we just did? That must be Q1 because 75% of the game is ahead. So we use the Q1 formula. Yeah?
So you only use that when, like, if you're speaking in terms of the game, there's still more of the game to go, but like for the other one, it was past the game, so like
right.
we're at the third quarter of the game.
Q3 is past halftime. Yeah, most of the game is over. If you're, yeah. So this must be Q3 here, I think. Yeah, 82.75 must be Q3. That's 3/4. So I really could have solved this whole problem by just saying, writing the Q3 formula and using 82.75. Would have got the same answer. Because that's the third quarter, which is past halftime. Either way would have worked. Good there? Does that make sense? So whenever you see 25% or 75% in any of these problems, think Q1 or Q3 every time. That's always, really, without exception. They want you to do something with Q1 or Q3 if they're bringing out a 25% or a 75% for sure. All right. Okay, a normal distribution has standard deviation 9.3 and 84% of the data fall above 48.1 centimeters. Find the mean mu. Okay, so now I got to give you the. I keep wondering how long I should hold off the whole story. All right, it's time to give you the whole story. All right, let's draw out. I need a little higher than that. So write this out. This will be really important for what we're going to do. Oops, I got to draw a little bit better. I'm going to draw the bell curve, and I'm going to fill everything in. All right, so there's the bell curve. Put the middle in there. Put a line right down the middle. This will be super. Basically, the rest of this whole chapter is going to be on this bell curve. It's that important. Everything we're doing in this chapter is all about this bell curve and the lines and the percentages and the things on the bottom involved in the bell curve. Bell curve, really important, practical, real-life kind of thing for statistics. So there's the middle. The middle is mu, as we've already said. The very middle is mu, the Greek mu, m. And then what we're going to do is we're going to go 3 lines to the right and 3 lines to the left. 3 jumps to the right, 3 to the left, evenly spaced. 1, 2, 3, and 1, 2, 3. 3 to the right, 3 to the left. The first one to the right is mu plus 1 sigma. The second one to the right is mu plus 2 sigma. And the third one to the right is mu plus 3 sigma. So those are the standard deviation jumps. That's what I was telling you about from line to line is sigma. See how from line to line it just goes up by a sigma every time? This is mu, add 1 sigma, add 2 sigmas, add 3 sigmas. So from line to line, the jump amount is sigma. Standard deviation. So if you go back a line, this is going to be mu minus 1 sigma. This is mu minus 2 sigma. And this is mu minus 3 sigmas. So from the middle, from the mu in the middle, make that a little bolder, from the middle, you go back 1, 2, 3 sigmas, or you go, so you subtract them, or you add to the right 1, 2, 3 sigmas. So every line, again, the jump from line to line is always sigma. To the right you add, to the left you subtract. From line to line. Okay. Now, the most important part of the normal curve, and I'll make this real in just a second. I'm sure you're still wondering, like, what is this weird looking thing? What does it have to do with the real world? We're about to get there. We are so close. Let me fill in the percentages. 34%, 34%, 13.5%, 13.5. And these are going to this will be the most important thing on your 3x5 card week after next at the final exam. 13.5, this one will be 2.3, that's a scribbling there, 2.35%, 2.35%, and the final area, 0.15%, 0.15%. Everybody good so far? Now, what in the world is this? This is what we call normal distribution. It's how things are normally distributed. Now, what do I mean? The numbers at the bottom could be anything, almost anything, in the real world. So, suppose I took men's shoe sizes. I have no idea. What's the average men's shoe size? I have no idea. Is it 8? 7, 8, 9? I don't know. Something like that. Let's just say 8. I'll just make something up. That's the middle. The middle's the middle's the middle, right? So let's say I'm just doing shoe sizes. I'll change it to something else in a minute. So men's shoe sizes. There is some average. I don't know what it is, but there is some average of all men in the entire world, or you can just take the United States or whatever you want. And there's an average. So say the average shoe size is 8. I don't know what it is. I'll just make up a number. Say it's 8. And then there's some deviation. Not every man has exactly an 8 foot, right? Some are bigger, some are smaller. There's deviation in that. Well, how much deviation? Well, some have a lot bigger feet. Some have a little bigger feet. Some have a lot smaller feet. Some have a little smaller feet. Right, it varies, right. But there is some average deviation called standard deviation. In other words, yeah, not everybody's right on 8. Some are way above 8. Some are a little above. Some are way below. Some are a little below. But there's an average off the middle, right? There's an average distance from the middle. That's called standard deviation. I don't know what that is. Let me just make it up. Let me say it's 2. So that would mean the jump is 2. So this would be 10. This line would be 10. So you would add 2. If the jump is 2 again, then you would add 2 again. This line here would be 12. And then the jump again, add 2 again. The jump this would be 14. Do you see what I'm doing? I'm saying there's some average shoe size, I don't know what it is, pretend it's 8 for men. And then and then there's some amount that everybody is off the average. Some are way above, some are a little above, some are way below, a little below. But there's an average amount off the middle. What is that? I have no idea, but you could go on Google in 2 seconds probably and get for me the average men's shoe size in America, probably, or maybe the world, I don't know. And the standard deviation. If you guys want to do it, feel free. Go on. You got it already? It's coming up, yeah. Find out, and they'll probably give you average and standard deviation. And average is average, and standard deviation is typical amount off the middle. Everybody understand that? You guys have a feel? This is where you really want to feel standard deviation. We're not going to calculate it, and that's what's most important in life, because you'll read real life statistics, they'll give you standard deviation. Is there something in your gut that happens? Yes, I feel sick to my stomach, Mr. Aaron. No, I mean, like, is there a feeling when you hear standard deviation? Typical amount off the middle. That's what that means. Average amount, not off the middle. So maybe it's 2. Maybe it's 2 sizes. I don't know. So then this would go up by 2. So this would be 8, 10, 12, 14. And then you go down the other way, down by 2, down by 2, down by 2. So this would be 6 and 4 and 2. So what? Well, if that's the case, and whatever Google tells us, whatever the real average is and real standard deviation for men's shoe sizes, what that means is then you can count on it that 34% of all men are going to have a shoe size between 8 and 10. That's what these percentages mean. Whatever the average is, whatever the standard deviation is, the percentages always hold. And 34% of the men are going to have a shoe size between 6 and 8. And put those two together, 34 and 34, 68% of men will have a shoe size between 6 and 10. Kind of average, right? From here to here, 68%. That means 68% of all men will have a shoe size between 6 and 10, meaning they're kind of average. Kind of average. They don't have super big feet or super small feet. They're kind of average. 68% of men. Now, there'll be some men that have larger than average shoe sizes. So maybe between 10 and 12, there'll be only 13.5% of men that'll be in that zone. There'll be very few men, 2.35%, that have a shoe size between 12 and 14. And there'll be very, very few men, 0.15%, that's less than 1%. It's a lot less than 1%, that have a shoe size bigger than 14. NBA kind of people. Shoe size bigger than 14. This makes sense. That's what that table, and then same thing on the other side for smaller feet. So now we could change the real life picture. Did you get it at all? Did Google ever tell you what the average shoe size was for men?
10.5.
Wow, I'm really way off. Okay, so 10.5. Is that average for America or American shoe size? Did it give a standard deviation?
No.
Oh, did it? Oh, that's okay. That's okay. Anyway, so I'm a little bit off in my thing. But yeah, you could probably just type in standard deviation, men's shoe size, you probably get it. But anyway, so let's change the thing now. Instead of men's shoe sizes, let's go with, what would be good? How about weight of leaves? It's fall, right? The leaves are all coming down. If I said, I'm going to pick the average weight of leaves on oak trees, in Fresno. I'm just showing you it's anything in nature. So if you went out and just grabbed all the oak tree leaves that have fallen down, and you put them all on scales to weigh them, it'd be a very tedious process, there would be some average. I don't know what it is. Let's just make up some numbers here. 10 ounces. I'm going to use 10 again because I like that number. Ounces. We're talking ounces now, maybe. 10 ounces. I don't know. And then there would be some standard deviation. They wouldn't all be the same. They would be different. Some bigger, some smaller, heavier, lighter. There'd be some average. Maybe it's 3 ounces. So then this would go up to 13. Next line would be 16. Next line would be 19. Go down the other way, 7, 4, 1. And you would find that 34% of all leaves are between 10 and 13 ounces. And on you go. And that's what we find is when you measure anything natural, any naturally occurring phenomenon, shoe sizes, leaf weight, size of your ears, length of your hair, size of poodles, whatever, any naturally occurring thing, we find its bell curve, which means what? Humped up in the middle, meaning most whatever is average. Is that making sense? That's what this bell curve is saying. In other words, it's not, maybe it'd help if I spread it out another way. Yeah, that probably this would help. What if I said, hey, yeah, I measured men's shoe sizes, okay, and there was some average. What was it, 10? Average shoe size was 10.5, let's just say 10. And some are bigger, some are smaller. And, it came out kind of level. In other words, men between 10 and 12 and 12 and 14, that's kind of scribbly, 10 and 14 and 14 and 16, and even to the right of 16 and bigger. It was even Steven, and then down here, this would be 8, 6, 4. So in other words, let's just say, how many is that? 1, 2, 3, 4, 5, 6, 7, 8 sections? What's 100 divided by 8? I don't know. 50, 25, 12.5. So let's just say it's like 12.5%, 12.5%, 12.5%, 12.5%, 12.5%, 12.5%, 12.5%, 12.5%, 12.5%. It just came out even, Steven. No way. And that's not the truth, right? What do I mean? There is not 12% of the population that has shoe size 16 and bigger, right? Most people are, and certainly not shoe size 4 or smaller, right? No way. What? Because it's a naturally occurring phenomenon. It's going to be humped in the middle, isn't it? Most any naturally occurring phenomenon is average. Mostly you get stuff near the middle. And then you get some extremes on the two ends, but it goes down quickly, doesn't it? That's what the bell curve is saying. Not only is it generally humped in the middle, as I keep saying, but it's very predictable. So predictable, in fact, that the percentages never change from example to example. 34, 34, 13.5, 13.5, 235, 235, 0.15, 0.15. They are super predictable for naturally occurring phenomenon, this pattern. Now, not always. Of course, there are some exceptions. But when they are fitting these percentages, they call that normal distribution because it's what normally happens for naturally occurring phenomena. Does that make sense? So there's the big picture. That's what we're really doing. So this is super useful to scientists and all kinds of people who measure things involving, also for social scientists who measure walking speed, IQ, anything mental as well, and behavioral. Same thing. We find average behavior, and then it goes down for different behaviors. Go down quickly. There's average behavior and different. Just social scientists use this too. Very, very consistent findings is that things that occur naturally fit these percentages. So for the rest of this section, what they're going to do is they're going to give us some real life situations, and they're going to say, blah, 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 IQs were measured, or men's heights were measured, or whatever, shoe sizes were measured, and the results were normally distributed. Whenever they use those words, normally distributed, they mean these percentages are there. So the numbers on the bottom change from example to example, whether you're talking about shoe size or weights or the weight of oak leaves. The numbers on the bottom change, but the percentages do not change. Is that making sense? Everybody hearing me on that? So I'll change the numbers on the bottom. I'll put the middle here, and I'll add the standard deviation 3 times to the right, subtract it 3 times to the left, but the percentages will never change. That's what it means to be normally distributed. Those percentages hold. And if you know that, you have a lot of power to be able to, all I would need, for example, with the men's shoe sizes, if you gave me the standard deviation, you told me the average was 10.5. If you gave me the standard deviation, so anybody get that? What's standard deviation? That's right, I don't know. But I could quickly find where 34% of all men in America were. If I just took whatever the average was, 10.5, and added the standard deviation, boom, I would know 34% of all. I would know percentages for, the breakdown of percentages for all of America, men shoe sizes, that quick, would fit that percentages. So you know a lot of information just from the middle and the standard deviation jump, because of the normal curve. Discovered by the greatest mathematician ever, Carl Friedrich Gauss, probably the greatest. Gaussian, so it's called the Gaussian bell-shaped curve. All right. So here we go. How are we doing? All right. We got 20 minutes. Let's answer the question. Ooh, so going back to the bell curve. Is it on your screen? Okay. Good. Going back to the bell curve. We'll put the bell curve here. And so you'll just draw this over and over and over again. Here's the middle. Now, did it tell me the middle? It didn't, did it? No. And then I'll do 3 jumps to the right. 1, 2, 3 jumps to the right. And 1, 2, 3 jumps to the left. Here's the middle. Here's the middle plus 1 sigma. Here's the middle plus 2 sigmas. Here's the middle plus 3 sigmas. Other way, same thing. I'm not going to bother right now. Standard deviation is 9.3. And now what are the percentages? 34. They're always the same, aren't they? 34, 34. 13.5, 13.5, and 2.35, and 0.15, 0.15. Okay, so now what they're saying is where, you want to spot where 84% of the data fall above. 84%. So when they say 84% above, they mean to the right. To the right. Above is to the right of 48.1. Okay, so hold on. Let me help you with how you get your bearings on the normal curve. So what they're saying is they're saying 84. So there's 2 things they're going to talk about on these problems. Percentages, which are up here, and non-percentages, which are down here. The numbers down here are not percentages, notice. There's no percentages on the ground level. No percentages down there. So 84% of the data fall above, to the right, of 48.1. Where's that 48.1 going to go? Is he a percentage? No, he doesn't have a percent symbol on him. He's not a percentage, so where is he going to go? Somewhere on the bottom. One of these down here will be the 48.1. See how I know to look for that? Because 48.1 does not have a percentage symbol on it. So it goes down here, doesn't it? You guys with me? Right? Percentages go up top. So as you're reading these problems, any number that does not have a percentage must be a number on the bottom. So that's what I know. So what are they saying? 84% is to the right of what spot? Can anybody already tell? I'd be impressed if you can already tell. Where must it be? The 34 on the left. Yeah, it must be right here. How do you know that? Well, think, how much is this? Think with me for a minute. How much is all that I just shaded? Just that. This is the middle. So how much is to the right of the middle? 50%. It's the middle, right? So this has got to be 50. I don't need to add up the percentages. I mean, you could do it. You could add 34, 35, 235, 0.15. Guess what you're going to get? 50%. Because that's half, right? If I say it's halftime, how much of the game's left? 50%, right? So this is 50%. All these is 50%. And then what's this? 34. So what's 50 and 34? 84. So all of this from here on must be 84%. So this is the spot they're talking about. This is the spot that has 84% going to the right of it, doesn't it? See how we came up with that? So when you see that 84, you want to think, oh, 50 and 34. They're talking 50 and 34. They're saying middle is 50, and then so it must be right here, because this is 34 and 50, so this is 84% to the right. Okay, so what? So that means I'm right here, and that's the 48.1. So right here must be 48.1. Remember, because 48.1 is not a percentage, so it's a number on the bottom. So 48.1 must be right here. Okay, so what? Well, this is the middle. This is mu. So what is this spot? Mu minus 1 sigma. It's 1 sigma to the left of the middle. Remember, every line, jump to jump, from line to line, it's a sigma jump. So if this is the middle, to the right is add 1, add 2, add 3 sigma. To the left is subtract 1. Subtract 2, subtract 3 sigma. So this is 1 jump to the left. So this 48.1 must be equal to mu minus 1 sigma. So there's our equation. 48.1 is mu minus 1 sigma. Let me get this other stuff out of the way. Do y'all see how I came up with that? 48.1, the number down here, must be 1 jump to the left of the middle, because it has 84% to the right. So 48.1, which is a number on the bottom because it's not a percentage, must be mu minus 1 sigma. Okay, so what? Well, they gave me sigma right here, 9.3. So 48.1 is mu minus 1, get this out of the way, times 9.3. I can solve for mu. Mu is the only letter left. I can solve that equation for mu. 48.1 is mu minus 1 times 9.3 is 9.3, right? How do you solve for mu? What do? Add the 9.3, right? And so mu equals, I don't know, 57.4? Oh yeah, that's right, 57.4. Done. That makes sense. So, every one of the problems from now on, the bell curve with the percentages, they say 84, you think, oh, that's the line 1 jump to the left, because that's 34 and 50, that's 84. So right down there, 48.1 must be 1 jump to the left, mu, middle, minus 1 sigma. Mu minus 1 sigma is 48.1. Put in the sigma, solve for mu. Good. Shall we try another one? Okay. Normal distribution, mu standard deviation. What percentage of the data fall below mu plus sigma? Well, normal curve every time, pretty much. So put the middle. Here's mu. 1, 2, 3 jumps to the right. 1, 2, 3 jumps to the left. Mu plus 1 sigma. Mu plus 2 sigma. Mu plus 3 sigma. Mu minus 1 sigma. Mu minus 2 sigma. Mu minus 3 sigma. 34%. 34%. 13.5. 13.5. 2.35, 2.35, 0.15, 0.15 every time. Okay, what's their question now? What percent, so percents are up above, is below? Below means left. You guys understand the below above thing? Right? If you're watching the football game, you know, below means what happened before, above means what happens later, to the right. Below is to the left, above to the right. Below mu plus sigma. Where's mu plus sigma? What number's in front of that? Mu plus sigma. It must be an understood 1, huh? There's no number there, so that means mu plus 1 sigma. So that's where? That's right here. Mu plus 1 sigma, huh? That's one jump to the right of the middle, isn't it? Mu plus 1 sigma, mu plus sigma. So they're saying, hey, what percentage is below left? What's all this percentage? They're saying. See what they're saying? What percentage is below one jump to the right of the middle? So what must all that percentage be? Well, this is half. From here to there, from middle left is half. That's 50%. And 34 more? It must be 84%. That's how I got that answer. Does that make sense? Just took 50 plus 34. And next question, what percentage is between 2 jumps and 1 jump to the right? That's right here, isn't it? Between 1 jump and 2 jumps. The 1 jump line to the, here's the middle, 1 jump to the right and 2 jumps to the right. How much is between those two? 13.5. Let's just read it off the chart. Does that make sense? You're starting to speak this language. The problems aren't hard if you can speak, if you understand their language, what they're saying. It's usually a pretty simple question. It's just all their language is a little hard to get used to. Does that make sense what they're saying? Between mu plus 2 sigma and mu plus, really that's 1 sigma. Between 1 and 2 sigma. 1 and 2 jumps to the right of the middle. 13.5% of the data. Good. I move on. Okay, so normal distribution, mean 12.4, standard deviation 3.1, plus 1% between 3.1 and 21.7. Okay. Same thing. There's really, like every problem, we need to, I'm going to make that a little bigger up there. Draw the bell-shaped curve again and again and again and again. Let's draw the bell curve. So here's the middle, 1, 2, 3 jumps to the right, 1, 2, 3 jumps to the left. So here's the middle. Now this time, I'm not going to fool around with putting the mu's everywhere. They gave me the mu. What is the mu? 12.4. So I'm just going to write 12.4 right there. That is, bless you, 12.4. And then the standard deviation, that's the jump amount from line to line, isn't it? Y'all tracking with me? So that means I can just add 3.1 and then add 3.1 again and then add 3.1 again. And then the other way, I will subtract 3.1, subtract 3.1, and subtract 3.1. So 12.4, add 3.1, what is that? 15.5, add 3.1, is that 18.6, add 3.1, 21.7. Good to there? See what I'm doing? I'm just adding 3.1, add 3.1, add 3.1. And the other direction, just subtract. Is that going to be 9.3 and 6.2 and 3.1? Yeah. And the percentages never change, do they? Remember, it's only the numbers on the bottom that change from real-life example to real-life example, leaves or min shoe sizes or whatever. But the percentages are always the same. That is the point of a normal distribution. It's normally distributed this way. So put those in. Those don't change, but the numbers on the bottom do. 2.35. Oops. What am I doing here? Just getting off. 0.15. Okay. So now, what's their actual question? Approximately what percentage, I've already answered the question, but suppose it wasn't there, fall between 3.1 and 21.7? Well, do you see those? Those are not percentages, so we look on the bottom for those, right? 3.1 right here, this line. And 21.7 right here, that line. So they're saying, what percentage is all of this? That's their question. Does that make sense? So I just put the middle on, 12.4 the mu, and then add the 3.1, add the 3.1, add the 3.1, because that's standard deviation, subtract 3.1, subtract 3.1, subtract 3.1. Then I find 3.1 and 21.7, and they're saying what percentage is between? So how do we figure out what percentage? Can we just add all those percentages? You could. There are some quicker ways. I mean, that's okay. But you know what you could do? What else could you do?
You gotta add the 0.15% on each side and subtract that from the whole.
From the 100, huh? Yeah, you could say, look, the whole thing's 100%, and you could just subtract the 0.15 and the 0.15, because the percentage in the middle is everything but the 2.15s, huh? That'd be a little quicker. I mean, you could add up all the ones in the middle, but that'd take longer. So you'd get 100% minus 0.3%, you'd get 99.7%. There it is. 99.7% of the data falls between those two. Does that make sense? On that? Right, I just did 15 cents, and 15 cents makes 30 cents. That's up 30 cents there, right? If you're subtracting 15 cents and 15 cents, you're subtracting 30 cents, which gives you $99.70. Good? Money might help. We deal with money all the time. We think better with money usually. Is that good on that? All right, let's do